What is relay in electronics/electrical, and how does it function? Relays are electromechanical switches used to control the flow of electricity in electrical circuits. They work by using a low power signal to control a higher power circuit. Here are a few examples of relay applications in electronics and electrical systems. In automotive applications, relays are extensively used for various functions due to their ability to handle high currents and voltages reliably. Here are some common automotive applications of relays. Headlights. Relays are often employed to control the headlights in vehicles. The headlight switch typically sends a low current signal to activate the relay, which then connects the high current circuit that powers the headlights. This setup helps prevent excessive current flow through the headlight switch, prolonging its lifespan. Starter system. In automobiles with larger engines or diesel engines, the starter motor requires a significant amount of current to crank the engine. Relays are utilized in the starter circuit to handle this high current. When the ignition key is turned to the start position, the relay is activated, allowing the high current from the battery to flow to the starter motor. Cooling fans. Many vehicles use electric cooling fans to regulate engine temperature. Relays are employed to control these fans, ensuring they operate at the appropriate times. Temperature sensors or engine control units, ECUs, send signals to activate the relays, which then turn on the cooling fans when needed. Fuel pump. The fuel pump in a vehicle is responsible for delivering fuel from the tank to the engine. Relays are commonly used to control the operation of the fuel pump. When the ignition is turned on, the relay receives a signal from the vehicle's electronics to activate, allowing power to flow to the fuel pump. Power windows. In vehicles equipped with power windows, relays are often utilized to control the window motors. When the driver or passenger activates the window switch, a low current signal is sent to the relay, which then supplies power to the window motor, allowing the window to open or close. Engine control systems. Relays play a role in various engine control systems, such as controlling the operation of fuel injectors, ignition coils, and other components. They help manage the flow of current to these critical engine components, ensuring proper engine performance. In all these applications, relays serve to control high current circuits with lower power signals, providing a safer and more reliable means of operation in automotive systems. In industrial automation, relays serve as fundamental components for controlling machinery, processes, and systems. Here are several key applications of relays in industrial automation. Motor control. Relays are extensively used for motor control in industrial automation systems. They facilitate the switching of power to motors based on input signals from sensors, programmable logic controllers, PLCs, or other control devices. Relays enable the start, stop, and direction control of motors, allowing precise control over industrial machinery such as conveyor belts, pumps, compressors, and robotic arms. Process control. Relays play a crucial role in process control applications within industrial environments. They are used to control the operation of valves, actuators, heaters, and other devices involved in industrial processes. Relays enable the automated regulation of parameters such as temperature, pressure, flow rate, and level within manufacturing processes, ensuring efficiency, consistency, and safety. Safety systems. Relays are integral components of safety systems in industrial automation. They are utilized in safety relay modules, safety controllers, and safety interlock circuits to implement safety functions such as emergency stop, machine guarding, light curtains, and safety door monitoring. Relays help ensure compliance with safety standards and regulations, protecting personnel and equipment from hazards in industrial settings. Sequence control. Relays are employed for sequence control, where the operation of multiple devices or processes needs to be coordinated in a specific sequence. Sequential relay logic circuits, also known as ladder logic, are used to program the sequencing of operations in industrial control systems. Relays switch between different states or steps in the sequence based on input conditions, timers, counters, or logic functions, enabling complex automation sequences to be implemented. Power distribution. Relays are utilized for power distribution and switching applications in industrial control panels and electrical distribution boards. They enable the selective switching of electrical loads, circuits, and power sources, allowing for efficient power management and distribution within industrial facilities. Relays help prevent overloads, short circuits, and other electrical faults by isolating faulty circuits and disconnecting power when necessary. Remote monitoring and control. Relays are integrated into remote monitoring and control systems for industrial equipment and processes. They enable the remote actuation of devices, such as turning equipment on off or adjusting settings, through communication interfaces such as Ethernet, Modbus, Profibus, or DeviceNet. Relays facilitate remote access, diagnostics, and troubleshooting of industrial automation systems, enhancing operational efficiency and maintenance capabilities. Overall, relays play a critical role in industrial automation by providing reliable switching and control functions for a wide range of applications, contributing to increased productivity, safety, and flexibility in manufacturing and industrial processes. In home automation, relays serve as essential components for controlling various household devices, systems, and appliances. They enable the automation, remote operation, and integration of multiple functions within smart homes. Here are several key applications of relays in home automation. Lighting control. Relays are extensively used for controlling lighting systems in smart homes. They allow for the remote switching on, off, dimming, and scheduling of lights throughout the home. Relays can be integrated with motion sensors, light sensors, or smart switches to automate lighting based on occupancy, ambient light levels, or preset schedules. They enable energy-efficient lighting solutions and enhance home security by simulating occupancy when residents are away. HVAC, heating, ventilation, and air conditioning control. Relays play a vital role in HVAC automation by controlling heating and cooling systems, fans, and dampers. They facilitate the remote adjustment of thermostat settings, temperature zones, and ventilation modes based on occupancy, time of day, or environmental conditions. Relays enable energy savings, comfort optimization, and indoor air quality management in smart homes. Appliance control. Relays are used to control a wide range of household appliances, including refrigerators, washing machines, dishwashers, ovens, and coffee makers. They enable remote start/stop, scheduling, and monitoring of appliance operation via smart home platforms or mobile apps. Relays help automate household chores, conserve energy, and provide convenience to homeowners by integrating appliances into smart home ecosystems. Security and access control. Relays are integrated into security and access control systems to automate door locks, gates, garage doors, and security cameras. They enable remote locking/unlocking, arming/disarming, and monitoring of entry points through smart home interfaces. Relays facilitate the integration of security sensors, alarms, and video surveillance into comprehensive home security solutions, enhancing safety and peace of mind for residents. Window treatments. Relays are employed for controlling motorized blinds, shades, and curtains in smart homes. They enable the remote opening/closing, tilting, and scheduling of window treatments to manage natural light, privacy, and energy efficiency. Relays can be integrated with light sensors, temperature sensors, or smart thermostats to automate window treatment adjustments based on environmental conditions or user preferences. Irrigation and outdoor lighting. Relays are utilized for automating irrigation systems and outdoor lighting in smart homes. They enable the scheduling, sequencing, and remote control of sprinklers, drip irrigation, landscape lighting, and garden features. Relays help conserve water, enhance curb appeal, and extend outdoor living spaces by integrating outdoor amenities into smart home environments. Overall, relays are integral to home automation systems, providing the switching, control, and integration capabilities necessary to create intelligent, energy-efficient, and convenient living spaces for homeowners. They enable the seamless integration of diverse devices and systems within smart home ecosystems, enhancing comfort, convenience, and sustainability. In electronic circuit protection, relays are utilized to safeguard electronic components and devices from damage caused by overcurrent, overvoltage, short circuits, or other electrical faults. Here are several key applications of relays in electronic circuit protection. Overcurrent protection. Relays are employed to protect circuits and devices from excessive current flow, which can lead to overheating, component damage, or fire hazards. Overcurrent relays monitor the current passing through a circuit and actuate when the current exceeds a predetermined threshold. They can open the circuit to interrupt the flow of current or trigger other protective measures such as activating circuit breakers or disconnect switches. Overvoltage protection. Relays are used for protecting electronic circuits and equipment from voltage spikes, surges, or transients that can occur due to lightning strikes, power grid fluctuations, or switching events. Overvoltage relays detect abnormally high voltage levels and trigger protective actions to limit the voltage or isolate the affected circuit. They may activate voltage clamping devices, such as metal oxide varistors, MOVs, or transient voltage suppressors, TVS diodes, to absorb excess voltage and prevent damage to sensitive components. Short circuit protection. Relays play a role in protecting circuits against short circuits, where an unintended connection occurs between 2 points of differing electrical potential, resulting in a sudden surge of current. Short circuit relays detect the abnormal current flow caused by a short circuit and quickly disconnect the affected circuit to prevent further damage. They help isolate the faulted section of the circuit and minimize the risk of fire or equipment damage. Ground fault protection. Relays are utilized for ground fault protection, which safeguards against electrical faults that occur when current flows from a live conductor to ground due to insulation breakdown or equipment malfunction. Ground fault relays detect the imbalance in current between the supply and return conductors and trip the circuit or activate ground fault interrupters, GFIs, to disconnect power and mitigate the hazard. Reverse polarity protection. Relays can provide reverse polarity protection for electronic circuits and devices, preventing damage caused by incorrect polarity connections of power sources or batteries. Reverse polarity relays detect the reversed voltage polarity and prevent current flow in the wrong direction by opening the circuit or reversing the polarity automatically. Thermal protection. Relays may incorporate thermal protection features to prevent overheating of circuits, components, or devices due to prolonged operation or excessive ambient temperatures. Thermal relays monitor temperature levels and activate cooling systems, thermal cutoff switches, or other protective measures to maintain safe operating conditions and prevent thermal damage. Overall, relays play a crucial role in electronic circuit protection by detecting abnormal operating conditions and implementing protective actions to ensure the reliability, safety, and longevity of electronic systems and equipment. They help safeguard against various electrical hazards and ensure the integrity of electronic circuits in diverse applications. In the context of relays, the input signal refers to the electrical or electronic signal that initiates the switching action of the relay. This signal typically comes from a control device, such as a switch, sensor, microcontroller, or programmable logic controller, PLC, and serves to activate or deactivate the relay based on specific conditions or commands. The input signal to a relay is usually a low-voltage, low-current signal designed to be compatible with the relay's coil specifications. When this input signal is applied to the relay's coil terminals, it generates a magnetic field that attracts or repels the relay's internal armature, causing the switch contacts to open or close. Here are some common sources of input signals for relays in various applications. Switches. Manual switches, such as push buttons, toggle switches, or rotary switches, can serve as input devices for relays. When the switch is pressed, turned, or toggled, it sends a signal to the relay coil to activate or deactivate the relay. Sensors. Various types of sensors, including proximity sensors, motion sensors, temperature sensors, light sensors, and pressure sensors, can provide input signals to relays based on detected environmental conditions or events. For example, a motion sensor may trigger a relay to turn on a light when motion is detected. Microcontrollers/PLCs. In automated systems, microcontrollers or PLCs are commonly used to provide logic control and generate input signals for relays. These programmable devices can process inputs from sensors or user interfaces and send corresponding signals to activate or deactivate relays as part of the system's control logic. Timers and sequencers. Timers, counters, and sequencers can generate timed or sequential input signals to control relay operations in a predefined manner. For instance, a timer may send a signal to activate a relay for a specific duration, while a sequencer may coordinate the activation of multiple relays in a predetermined sequence. Communication interfaces. Relays in networked or remotely controlled systems may receive input signals through communication interfaces such as Ethernet, RS-232, RS-485, Modbus, or CAN bus. These signals can be transmitted from central control systems, remote terminals, or wireless devices to command relay actions. Overall, the input signal serves as the trigger for the relay's switching function, allowing it to control the flow of current in electrical circuits based on external stimuli, commands, or programmed logic. The electromagnetic coil is a crucial component of a relay, responsible for generating the magnetic field that actuates the relay's switching mechanism. It consists of a coil of wire wound around a core material, typically made of ferromagnetic material such as iron or steel. Here's how the electromagnetic coil functions within a relay. Application of voltage. When a voltage is applied across the terminals of the electromagnetic coil, an electric current flows through the coil. The direction of current flow determines the polarity of the magnetic field generated by the coil. Creation of magnetic field. According to Ampere's law, when an electric current flows through a conductor, it creates a magnetic field around the conductor. In the case of the relay's electromagnetic coil, the current flowing through the coil generates a magnetic field around it. Attraction or repulsion of armature. The magnetic field produced by the coil interacts with the ferromagnetic armature or core within the relay. Depending on the design of the relay, the magnetic field either attracts or repels the armature. Switching mechanism. The movement of the armature due to the interaction with the magnetic field triggers the switching mechanism of the relay. In a typical relay, the armature is mechanically linked to the relay's switch contacts. When the armature moves, it either opens or closes the switch contacts, thereby controlling the flow of current in the relay's output circuit. Latching or non-latching operation. In some relays, the armature remains in its switched position even after the input voltage is removed, resulting in latching operation. In others, the armature returns to its original position when the input voltage is removed, resulting in non-latching operation. Energy consumption. The operation of the electromagnetic coil consumes electrical energy, which is dissipated as heat due to the resistance of the coil wire. The amount of energy required to energize the coil depends on factors such as coil resistance, voltage applied, and duration of activation. Overall, the electromagnetic coil is the primary component responsible for converting electrical energy into magnetic energy, which in turn activates the switching mechanism of the relay, allowing it to control the flow of current in electrical circuits. The contact mechanism is a fundamental part of a relay that governs the switching action of the electrical contacts within the relay. It consists of movable contacts, stationary contacts, and an actuating mechanism, all of which work together to establish or interrupt electrical connections within the relay. Here's how the contact mechanism functions in a typical relay. Movable contacts. These are metal components that can be physically moved to make or break electrical connections within the relay. Movable contacts are typically attached to an armature or relay switch mechanism and are designed to move in response to the application of a magnetic field or mechanical force. Stationary contacts. These contacts remain fixed in place within the relay and serve as the terminals for electrical connections. Stationary contacts are typically made of durable materials such as silver, gold, or copper alloys to ensure reliable electrical conductivity and longevity. Actuating mechanism. The actuating mechanism is responsible for moving the movable contacts in response to an external stimulus, such as the application of voltage to the relay coil or the activation of a mechanical switch. In electromechanical relays, the actuating mechanism is usually a magnetic field generated by the relay's electromagnetic coil, which attracts or repels the armature to move the contacts. Switching action. When the relay is energized or activated, the actuating mechanism causes the movable contacts to move into contact with the stationary contacts, completing an electrical circuit. This is known as the closed or make state of the relay contacts. Conversely, when the relay is de-energized or deactivated, the movable contacts return to their original position, breaking the electrical connection between the contacts. This is known as the open or break state of the relay contacts. Contact materials and design. The materials used for the contacts and their design play a crucial role in determining the relay's performance characteristics, such as contact resistance, contact bounce, and contact life. Contact materials must be selected based on factors such as electrical conductivity, resistance to arcing and welding, and resistance to mechanical wear. Contact arrangement. Relays may have different contact arrangements, such as normally open, NO, normally closed, NC, or changeover, CO, contacts, depending on the intended application and switching requirements. These arrangements dictate the initial state of the contacts when the relay is in its resting state and the state they assume when the relay is activated. Overall, the contact mechanism is integral to the operation of a relay, enabling it to switch electrical circuits on and off reliably and efficiently in response to control signals or external conditions. The output circuit of a relay is the portion of the relay where the controlled electrical contacts are located. It's where the relay's switching action connects or disconnects the load or device being controlled. The output circuit typically consists of stationary contacts, movable contacts, and terminals for connecting external circuits or loads. Here's how the output circuit functions in a relay. Stationary contacts. These are fixed contacts within the relay that provide the terminals for electrical connections. They remain stationary and do not move during the relay's operation. Stationary contacts are typically made of durable materials such as silver, gold, or copper alloys to ensure reliable electrical conductivity and longevity. Movable contacts. These contacts are connected to the relay's switching mechanism and can be moved to make or break electrical connections with the stationary contacts. The movement of the movable contacts is controlled by the relay's internal mechanism, such as an armature or a switching device. Load or device connection. The output circuit of the relay is connected to the load or device that needs to be controlled. This can be any electrical component, such as a lamp, motor, solenoid, heater, or other electrical appliances or equipment. Switching action. When the relay is activated or energized, the movable contacts move into contact with the stationary contacts, completing an electrical circuit between the relay's terminals. This allows current to flow through the output circuit and power the connected load or device. Conversely, when the relay is deactivated or de-energized, the movable contacts return to their original position, breaking the electrical connection and disconnecting the load or device. Contact rating. The output circuit of the relay is designed to handle specific electrical loads based on factors such as voltage, current, and power rating. It's important to ensure that the relay's contact rating matches the requirements of the connected load to prevent overheating, arcing, or damage to the relay contacts. Protection features. Some relays may incorporate protective features in the output circuit, such as transient suppression diodes, snubber circuits, or varistors, to suppress voltage spikes, surges, or other electrical disturbances that could damage the relay or connected devices. Overall, the output circuit of a relay serves as the interface between the relay and the load or device being controlled, allowing the relay to switch electrical circuits on and off reliably and safely in response to control signals or external conditions. In summary, relays play a crucial role in various electronic and electrical systems by providing a safe and reliable means of controlling high-power circuits with low-power signals.